Hello everyone, thank you for being here. Today I'll be presenting on a topic scaling conversational AI, SRE challenges and solution for high availability CCA systems. CCA systems are increasingly used to handle millions, even billions of customer interactions every day. These systems power virtual agents, automated chat responses, voice recognitions, and much more. With this scale, reliability becomes absolutely critical. In this session, we'll explore the unique site reliability engineering challenges in CCAI and the proven strategies to overcome them. From observability frameworks and automated remediation to progressive rollouts and chaos testing. I'm excited to share the practical lessons and battle-tested techniques that can help build more resilient AI-driven platforms. The CCI Reliability Challenge. Let's start by understanding the scale and constraints we operate under in CCA systems. We aim for 99.99% uptime. That's just over 5 minutes of downtime per month. This is a non-negotiated standard for enterprise systems, especially when we are dealing with customer interactions. Another key requirement is latency. Our target is maximum of 300 milliseconds response time. This is incredibly tight for systems powered by heavy NLP models and multi-service dependencies. With automation, we've been able to reduce MTTR, mean time to recovery, by 73%, which is a huge win in improving customer experience and operational efficiency. Unlike traditional web apps, failures in CCA are immediately visible. They can frustrate customers, cause escalated, and directly impacting business KPIs. What makes CCI even more challenging is the unpredictable nature of traffic and the complex web of integrations like CRMs, speech systems, third-party APIs, etc. Plus, the AI models themselves are not easy to interpret. They are black boxes in many ways. This all adds up to a very unique reliability challenge, which we'll be discussing in the next slide. Traditional monitoring limitations. Traditional monitoring tools were never built with AI systems in mind. For instance, transformer-based NLP models, which power intent recognition and response generations, are essentially black boxes. We can't inspect their internal states easily. Tools that work well with microservices often fail here. Another big problem is load patterns. CCA systems don't follow typical usage trends. You might have traffic spikes during product launches, seasonal sales, or even random social media trends. Threshold-based alerting doesn't work well because it can't predict or adapt to these irregular patterns. Then there is the issue of complex dependency chains again. CCA sessions might involve APIs, databases, voice engines, third-party integrations, etc. A small failure in one backend can ripple through the entire AI stack, and traditional monitoring might not have been able to detect this. That's why we had to build a new AI observability model, which we'll be discussing in the next slide. CCAI Observability Framework. To solve these gaps, we developed a 4-layer observability framework tailored for CCAI systems. 1. Business impact metrics, like conversation completion rates and CSAT, customer satisfaction. These tell us if users are getting what they need. 2. Model performance metrics. We track intent accuracy, fallback rates, and entity extraction quality. These gives us insights into how well the NLP models are performing. System performance. Here, we look at latency, error rates, throughputs, etc. These are all the traditional SRE metrics. 4. Infrastructure health. This is about CPU, memory disk usage, and system saturation. By combining all of these, we can map a symptom like an increase in fallback response to its root cause, whether it's a model drift, a backend slowdown, or infrastructure issue. This observability model helps bridge the gap between business impact and technical telemetry. Moving on to the next slide. Automated remediation strategies. Now, even with great observability, incidents will happen. So our next priority is automated remediation, reducing the recovery time when things go wrong. Our process starts with anomaly detection. Using ML-based pattern recognition, this lets us spot unusual conversation flows or system metrics in real time. Then we triage and classify the issue automatically based on patterns we learned over time, like intent degradation or resource starvation. Once classified, we trigger a remediation action. This might involve scaling up, rerouting the traffic, throttling, or even restarting specific services. And finally, we have a feedback loop. Each incident teaches the system something new every time, improving future detection and resolutions. This automated approach has helped us reducing the MTTR by more than 70%, which means user barely noticed something went wrong. Scaling strategies for peak loads. Let's talk about scaling, particularly during peak loads. Traffic spikes in CCA systems are hard to predict, but not impossible. We use predict autoscaling to anticipate these based on historical data and events. Next, we use token-based throttling, a fine-grained way to control the number of conversations being processed, preventing overload while prioritizing the high-value queries. We also implement conversation sharding, distributing different conversations to different clusters or shards. So no single resource pool gets overwhelmed. And during extreme loads, we use model optimizations like switching to lightweight models or reducing precision temporarily to maintain responsiveness. All of this helps us keep latency under 300 milliseconds even during 10x traffic bursts. Moving on to the next slide. Common CCA patterns. Through our operational experience, we identified several recurring failure patterns unique to CCAI again. Intent classification degradation. This often happens gradually. A new product name or slang throws off the model, and accuracy drops over time. Latency amplification cascades. A small backend delay gets compounded as the AI pipeline processes it, leading to exponential latency. Resource starvation. A single edge case user query might consume excessive memory or CPU affecting all sessions. Dependency chain failures. When a single external API or a backend service goes down, it can take down the entire conversational flow. Knowing these patterns helps us build better detection, alerting, and chaos testing frameworks, which we'll be discussing in the next slide. Chaos engineering. This brings us to chaos engineering, but with a twist, one that's tailored for AI. Our goal is to proactively test what happens when things go wrong in the AI layer specifically, not just infrastructure again. We stimulate scenarios like corrupted conversation memory, misclassified intents in a sequential order, or even model component failure due to memory overflow. Again, now the process involves forming hypotheses about failure modes, designing targeted chaos experiments, executing them with safety controls, and then analyzing the results and hardening the system. This AI-focused chaos engineering helps us prevent unknown failure modes from surprising us in a production. Progressive deployment models. All models evolve fast, but deploying them safely is also very crucial. So we use progressive deployment modes. First, we do shadow testing, where a new model runs alongside production but doesn't serve real users. We compare results quietly. Next, we move to a canary deployment, where a small slices of traffic is routed to the new model, where we monitor closely again. Then we gradually expand traffic based on performance metrics and confidence level, often adjusting during business hours to minimize the impact. If anything goes wrong, we have automated rollback mechanisms in place. Once we validated everything, we move to a full deployment. This staged rollout ensures we're innovating safely without affecting the end user experience. Moving on to the next slide. SLIs and SLOs for cost optimization. Let's now talk about how we balance performance with cost. SLOs, or service level objectives, don't just help ensure reliability. They also help us avoid over-provision. By carefully tracking metrics like response latency, query throughput, resource utilization, and intent accuracy, we can right-size our infrastructure. For example, if a model performs just as well with 50% fewer GPUs, during off-peak hours. That's a massive cost saving. Across the board, we've seen 30 to 40% cost optimization by aligning SLOs with actual user needs and system capacities. Moving on to the next slide. Building reliable CCAI key takeaways. To wrap up, here are the key takeaways for building reliable CCAI systems. Observability must include AI-specific and business-level metrics, not just CPUs and memories. Automation is key. Self-healing systems drastically reduce downtime. Use balanced SLOs to avoid unnecessary cost or effort while still maintaining a great experience. Finally, progressive deployments. Progressive deployments are very critical for rolling out changes without breaking user flows. These strategies help us build systems that are both innovative and reliable, the foundation for enterprise-scale conversational AI. Thank you all for your time and attention. I hope this session gave you a useful insight into unique reliability challenges of conversational AI systems and how SRE principles can address them. I'm happy to take any questions or feel free to connect with me later for deeper discussions. Let's continue building AI that's not only smart, but also resilient, scalable, and productive ready. Thank you all. Bye-bye.